In Lesson 8.9, Representation of Functions by Power Series, we are going to take rational functions and transform them into the sum of a geometric series. Of course, you remember that the sum of a geometric series is simply a over 1 minus r. So hopefully that won't be too difficult. Once we have our function written as a sum of a geometric series, we'll pull apart the a and the r and actually create the power series or the geometric series that represents that sum. Finally, we'll go ahead and find out the interval of convergence of that power series using the methods that we learned in previous lessons. So, with all that being said, let's go ahead and take a look at the method that we will use to accomplish everything I've said. So, when you are given a rational function and you want to write it as a power series, all you really need to do is follow this very simple two-step procedure here. The very first thing we're going to do is we're going to turn our function into a geometric sum. Now, just saying that might not be enough. Remember that the geometric sum is going to be of form a over 1 minus r. A over 1 minus r. Now, what's very important about that is that this must be a 1. Alright, it can't be a 5, can't be any other constant, it must be a 1. And the other thing to remember is that it's 1 minus r. Now, r is the term that will have the x in it. That will be the ratio once we turn that back into a geometric series. So, be very careful of those two things. Also, what we need to remember is that this will be centered at c. And when c is 0, that's all fine and dandy. But if c is some other value, then we will need to incorporate that into our ratio here. And I'll show you what I'm talking about when we get into our example problems, but those are just a couple things to be aware of. Now, once your function is written as a sum, then all we need to do is to write it as its constituent series. And the way we'll do that, this should be no surprise to you, it will be the sigma of a times r to the nth power. Remember that that is a geometric series right there. And so, again, this is a simple two-part procedure, but we might find out that there is a lot of tediousness and algebraic manipulation along the way. So we always need to be very careful, pay attention to details, and let's take a look at our first example. I must now admit to you that the first step in the procedure I just showed you, where we turn the function into the sum of a geometric series, is not always as clear-cut as I might have made it sound. In fact, even within that one step, there's a set of procedures to get you where you need to go. But let's explore that as we turn this function into a geometric series sum. To do that, of course, I need to turn it into a over 1 minus r. And the way I'm going to begin with this is by moving this x term over so it's in the r spot. Essentially, I'm going to reverse the denominator. Now, I can do that by multiplying both the numerator and denominator by -1. And if I do that, I'm going to end up with 4 over 5 minus x. And now, the denominator is kind of in the correct form. Something minus the radius. Well, down here I have 5 minus x. I'll deal with turning that 5 into a 1 in just a moment, but before I do, remember that I need to center this term at c equals -2. And so in order to do that, I'm going to turn this x right here, this x actually needs to say x plus 2. Alright, so what can I do to turn x into x plus 2? It might be a little easier than you're anticipating, but I can literally just write it as x plus 2. So long as I go ahead and balance out the fact that I just stuck a 2 in there. Now, be careful. I did not just add 2. Because of the minus sign in front, I actually just subtracted 2. And to make up for that, I am going to add 2 just to restore balance. Feel free to simplify the denominator and see that I'm not just blowing smoke here. Alright, so the last thing, well, not the last thing, but if I do combine my like terms, what I'll have so far is 4 over 7 minus quantity x plus 2. So far, so good. The one thing I have left to do is I need to turn this 7 into a 1. So what can I do to turn 7 into a 1? Well, hopefully you realize that all I really need to do is divide that by 7. But if I divide that by 7, I need to divide everything by 7. And so what my final rational thing here is going to say, and this isn't going to be pretty, but it's going to say 4/7 divided by 1 minus the quantity x plus 2 divided by 7. Now that might look like a big, giant mess. But, like I said, go ahead and simplify it and don't see if it equals the same function that I had at the very beginning. Except you'll notice that this one is centered at -2. So that kind of makes everything happy for us, if you will. Now, having done this, we should be able to identify that 4/7, that is our a value. And this x plus 2/7, that right there is our r value. So what I'm going to do now is going to go ahead and write this as a series, the geometric series that I was referring to earlier. It'll be the series from n equals 0 up to infinity. And my a value is going to be 4/7. And my ratio is simply going to be x plus 2, quantity, divided by 7. To the n power. So that is the geometric series that represents my original function. And at this stage, I would be finished if not for the second part of the directions, which state that we need to find the interval of convergence for this. So remember that an interval of convergence is actually just doing the ratio test. And if I do the ratio test here, let me go ahead and do this. I'm going to have the limit as n approaches infinity of my next term, which is going to be 4/7. Up on the numerator, I'll have x plus 2 to the n plus 1th power. And in the numerator, I will have 7 to the n plus 1th power. And of course, you could put those 7s together, call it 7 to the n plus 2, if you like, although it's not completely necessary. My current term, which I'm dividing by, so I'll do the reciprocal, is 7 times 7 to the nth power, or 7 to the n plus 1 if you like. And then quantity x plus 2 to the nth power on bottom. So once I simplify that, because this is the ratio test, I want that to be less than 1. And so let's go ahead and simplify and see what happens. Hopefully it's easy to tell that this 7 and this 7 will cancel. This 4 and this 4 will cancel. That just makes sense. All the constants have canceled and are gone. So on top, I'm going to have x plus 2. Again, that's to the n plus 1. This is to the n, so I'm just left with 1. And my 7s will look like that. Now, fortunately, I don't have any n's left. So what I can do is kind of go ahead and get rid of this limit situation here. I will end up with the quantity x plus 2 is less than 7. And so, of course, 7 is going to become my radius of convergence. And because 7 is my radius of convergence, what I'm going to end up with when I apply that to the center, which of course was -2, if I have -2 minus 7, that will give me -9. And if I have -2 plus 7, that will give me 5. Alright, so what I don't know is how my bounds are going to look, but I'm going to leave this as an exercise to you. Feel free to plug these values in for x and check whether they converge or diverge at the boundaries of this interval. Or, if you like, remember that this is a geometric series. And remember what happens when a geometric series has a ratio of 1. That's right, you can take these values of x, stick them back into your geometric series, and see if they work. Now, like I said, I'm going to leave this to you to decide. But what I will tell you is that our final answer will be the interval -9 to 5, non-inclusive of the endpoints. This here will be my interval of convergence. Feel free to check for yourself and see that this is in fact true. And then when you're ready, let's proceed to our next example. In our second example, you'll notice that we're trying now to center our series at 0. You'll come to appreciate this fact as you're working on your homework. When a series is to be centered at 0, it saves you a lot of trouble and some work as well. So we do have the same problem that we had in the first example, however, and that is that the x term is written first in the denominator. Remember how we resolved that in our first example. We simply multiplied the numerator and denominator by -1, and that is exactly what I'm going to do with this problem as well. And there we go. Now we're written in the form something over something minus r. So I can see that so far it looks like r is going to be this, but we'll see what happens. This is the stage in the first example where we went ahead and recentered our series by simply changing x into x minus h. That won't be necessary here. That's a great thing. So what we can do is just go ahead and fix the fact that we need this to say 1 minus r, not 5 minus r. So how am I going to fix that? Well, again, just like the first example, I'm going to divide everything by 5. Divide the numerator by 5, divide the denominator by 5, and there we go. Now, this function is written as a sum of a geometric series, and that's a beautiful thing. I can see that my a is going to be -1/5, and I can see that my r is actually going to be 2/5 x, or 2x over 5, if you like. So, this being the case, let's go ahead and write our series. This will be the sum from n equals 0 to infinity of a, which is -1/5, multiplied by r, which I will write here, r, to the nth power. And that is going to be our series. Now, in order to check for convergence or divergence, remember again that our center is at 0. Don't forget that fact. That's a very important fact. And let's go through and find what our radius of convergence will be. Remember that little r in this case represents a ratio of the geometric series, and I'll use capital R in this case to represent the radius of convergence. They are different. So let's go ahead and do our ratio test. Here's the limit as n approaches infinity. I am going to skip this -1/5. You saw in the last example that the constant just divided itself out, so I'm just going to go ahead and skip that part. And what I will write is my next term in the series, which is quantity 2x to the n plus 1 divided by 5 to the n plus 1. And I did split that up just for the sake of simplification here. And I will multiply that by the reciprocal of our current term in the series, which is, as you see it here. Of course, that will need to be less than 1 in order to converge. So, a little bit of simplification. You should be able to simplify this on your own by this point in time, of course. But it actually looks like we're going to come up with 2x over 5 is less than 1. Now, what's the beautiful thing here? Just like in the first example, this limiting term is now unnecessary. And what we're going to end up with is that the absolute value of x is going to be less than 5/2. Multiply by 5, divide by 2, and you see it. So, our radius of convergence we just found is 5/2. Just for fun, let's go ahead and actually see if the endpoints of this do converge or diverge. Of course, since my center is at 0, my lower bound will be at 5/2, and my upper bound will be at positive 5/2. And I just need to figure out whether to include or exclude those from my interval of convergence. Let's go ahead and try this out then. Let's say that x actually is -5/2. If that's the case, then my series is going to be -1/5. Plug in -5/2 for x, and you'll see that this will be -1 to the nth power. Now, in this case, we do have a geometric series. We have that our ratio is -1, and what does that mean? That means that this will diverge. -5/2 is not in our interval of convergence. Oh, that was fun, so let's try that one more time. This time, let's say x is positive 5/2, and see what wonderful things ensue here. We still have a, but when I plug 5/2 in for x, look what happens. Wow, my ratio just becomes 1. And when the ratio of a geometric series is 1, what can we say about that series? Same as we said when it was -1. This series is also going to diverge. So, here is my interval of convergence. you can see that neither of the endpoints do converge, so it's everything within those, using this as my series that represents my original function. Good times. Well, what happens when the original function is not quite so easy as you've seen in the first two examples? In the second example, you'll notice that the denominator is in fact a quadratic. Does this work with quadratics? Well, I'll tell you that it doesn't, but in the third example, I will show you how to resolve that situation as well. And so, as promised, here is our quadratic function. We can't really turn this into a power series. Power series only tend to work when we can make the function look like a geometric sum. That means that the denominator has to say 1 minus r. And how are we going to get this thing to say 1 minus r? Well, actually, we can get it to say 1 minus r. It's just that we're going to have to split this into two fractions. And if you haven't figured it out yet, what's coming up? It's a partial fraction decomposition. Always a good time. Let's see what this is going to look like here. If I do a partial fraction decomposition, I am going to skip some of my steps. But what I will end up with is 4x minus 7. The correct factoring, I should say, of the denominator in this case is in fact quantity 2x minus 1 multiplied by quantity x plus 2. So, my partial fraction decomposition, 4x minus 7, will equal x plus 2a. And then we'll follow that with plus quantity 2x minus 1b. Now, I'm not going to go through all the steps of this. This should be pretty easy for you to do by now. I will say this. One of the things I might do is let x equal negative 2, simply because that will cancel my a out. And if I do this, I'm going to get negative 15. Over here, I will get negative 5b. And so what I find out here is that b is in fact 3. And one more time, if I let x be 1/2, that will eliminate the b term over here. And if I do this, what I will end up with, I'm looking down at my notes to do this, but I'll end up with negative 5 equals, and then over on the right side I will have 5/2 a. And clearly that means that a will have to be negative 2. Alright, so those are my a and b, and now I understand that this original function can actually be written as the sum of two fractions. And if I do that, let's see what this would look like here. What I will end up with is 3 over x plus 2. Again, that's the b term over its fraction. And then the other fraction will simply be minus 2 divided by 2x minus 1. So you can verify for yourself that this partial fraction decomposition does equal the same as the original function. And so what I'm going to do is actually try to make a power series out of this right here. That will be doable. These both look like my examples A and B. So let's go with this and see what happens. I'm going to start with this fraction right here, this 3 over x plus 2. What I'm going to do is I'm just going to rearrange that. I don't need to multiply by negative 1 on top and bottom because it is positive on the bottom. So I get 3 over 2 plus x. Now you see the problem with that. It has to be a over 1 minus r. 1 minus r. So what I will do is I will turn this into 3 over 2 minus negative x. Now it is a over something minus r. Well, of course, I do need to divide by this 2 right here in order to make it 1 minus r. And so what I'm going to end up with is 3/2 divided by 1 minus, and then this will be negative 1/2 x. So there is my sum. From here, you can notice that the top is a, and this term down here is r. And that will enable you to make a power series out of that fraction. Now, if we take a look at the other fraction, let me draw a divider here. If we take a look at this fraction, this one I do need to rearrange the denominator. So I'll multiply the top and bottom by negative 1, which gives me that. So I want to say so far so good. But in actuality, if you take a look at this right now, I think this actually is the way that we want it to be, is it not? Yeah, I believe so. The only issue here, when I divided by, or when I multiplied the top and bottom by a negative, that will affect this negative up here. So it will change the terms around a lot. Instead of my new function being a fraction minus, or a series minus a series, the two negatives will affect each other. So we'll see what happens there. But that notwithstanding, it looks like I have my A, which I will put in blue here. It looks like I have my A, and it does look like I have my R. So what is my power series for this going to look like? I argue that our original function f of x can be approximated by the sum from n equals 0 to infinity of my first series, which if I do a times r to the n power, that's simply going to say 3 halves. R will be negative 1/2 x to the n power. Alright, so that's my first one. I would subtract by my next series, but because a is negative on my next series, I can just go ahead and add, and it'll work out just fine. Again, this is from n equals 0 to infinity. My a in this case was negative 2, but now it's just positive 2, and my r will be 2x to the n power. So, right there is going to be my power series that approximates this rather ugly function, I would say. Now, as far as finding the interval of convergence, again, I'm going to leave this as an exercise to you. My advice to you is to first find the radius of convergence for the first series, this one right here. Then go through, find the radius of convergence for the second series, this one. Then all you need to do is find out where they overlap. The smaller of the two radii, since they're both centered at 0, they are concentric. So the smaller of the two radii will apply to both series. Once you have that, you can check the endpoints and find the interval of convergence that way. So go ahead, pause this video, give that a quick shot. I'm going to go ahead and reveal the answers here because you should know what is correct. But again, like I said, pause the video, try it first, and then come back. Alright, so if you did pause the video, hopefully you do now know the correct interval of convergence. I will tell you, without showing all the work, that the radius of convergence for this part right here, the radius of convergence here is actually 2, while the radius of convergence here is actually 1/2. Now, that's not saying whether the 2 or the 1/2 are actually in their intervals. That wasn't relevant yet. But clearly this has the smaller radius, and so that's the one I'm going to use. If I set up my interval, it'll be centered at 0, so it will go down to negative 1/2, up to positive 1/2, and now, again, pause the video if you haven't done this yet, and find out whether these two endpoints are within the interval of convergence. I'll wait. Alright, so hopefully you've gone through and determined now that neither one of these are actually contained within the interval of convergence. It does force this series to diverge, although this series does still converge, this series diverges, and therefore the entire thing will diverge. Remember, it's just a geometric series, so when you plug the endpoints in, you're going to get 1 or negative 1, and that's not going to work for a convergent ratio. So, hopefully you see that forming power series, finding their intervals of convergence, is not a particularly difficult thing to do, although I will admit it is a rather long and tedious thing to do, which is why your homework is very short for this particular lesson. Also, fortunately, you won't have to deal with anything like this third example until late in the homework assignment. The last 1 or 2 problems are like this, but the rest of them are fairly simple. So, keeping all this in mind, remembering that all you're really doing is turning the function into the sum of a geometric series. Remembering that fact makes everything a lot easier. So keep that in mind, and good luck on this assignment.